Okay, let's get started for today's session. We are into week number 14 of the semester, which means that after today we'll be left with last 2 weeks of the semester, right? So from the viewpoint of technical content, we were looking at object detection using deep learning, right? And I explained to you in the previous session that what actually is the difference between object detection and what we have been doing previously, right? So in the first few minutes, just a quick recap so that we are in we have the tempo to go forward. So initially we have been solving only the classification problem, right, where we have an image, there's an object in the image, and we have to tell what object is present. Okay, that was typical classification problem that we have been solving using a typical CNN, right? But then we extended classification to classification plus localization, where we assume that image still has a single object, but not only we need to give the label of that object, we also need to tell what is the location of that object, right? So for the location, we discussed in the previous lecture, we need to output four numbers, right? X and Y coordinates of the center of the box or the top left corner of the box. It depends what convention you are using, as well as the width and height of the box. So for the classification, we use our existing machinery, the CNN, right? And for localization, since we have to predict four numbers, so we use a regressor, right, which outputs four numbers which define the bounding box. So then we extended this idea of classification plus localization, in which we only have a single object, right? Because this is a constraint which is hard to meet in, you can say, real world scenarios, right? So when we say object detection, in object detection we can have multiple objects within the same image, right? So you can have multiple objects within the same image. So if this is your image, so you need to have bounding boxes of all the objects which are present in the image along with the class label, right? So within that, I think last week we completed this RCNN, right? So in the next slide, I'll show you a quick review of RCNN, because based on that, our today's discussion will progress. So today we'll try to see fast RCNN, this, then faster RCNN, and then maybe towards the end we'll see FCN, which is for semantic segmentation. Okay, so this is the object detector. This was the first object detector, which was actually application of deep learning to object detection problem, which was RCNN that we had seen in the previous week, right? So a quick recap that how it works. Uh, you input an image, right? And then you use some external algorithm. For example, they are using selective search, which will generate regions of interest. Now, what are regions of interest? These are the regions which contain blobs, right? And they are likely to contain some object. So normally from the image, they generated nearly 2,000 such boxes of different sizes, and of course there's a lot of overlap between these boxes, because at this point in time they do not want to miss anything, right? Even if there are some boxes which do not contain any object, it is okay, right? But we don't want anything to be missed. That's why this number 2000 is a bit high, right? Because it is highly unrealistic that you will have such a high number of objects within a single image, right? So the idea is to have a very high recall. Then once you have these proposal, we said a CNN is fine tuned to learn features which are extracted from each of these boxes, right? And before feeding each of these proposals to the CNN, you need to resize the box to match the input of the CNN, right? For example, they are using a modified form of AlexNet, which accepts 2 to 7 by 2 to 7 by 3. So whatever is the size of the box, okay, it was resized to match the input layer, and then this CNN was fine-tuned. And once you have feature vector for each of those box, right? So those feature vectors are used to train an SVM, which performs the classification, right? And then once classification has been done, since the region proposal box cannot be or is not likely to be perfectly containing the object. So there is a bounding box regression which will adjust this box so that the object is fully contained within this box, right? Because the box can be shorter, it can be longer. So this bounding box regression will actually maybe expand or shrink in some directions the box so that it contains the object fully within that box, right? So this was RCNN which we had seen, and we identified many problems with that. And I'll show you in the next slide what are the problems. I'll give you a recap, but all of those problems were addressed in the subsequent paper by the same author, which was in the very next year, which was called Fast RCNN, right? And the objective was that the objective was that they wanted to speed up and simplify RCNN, right? Because it was very slow and it had to train three different models, right? Now, what were the bottlenecks in RCNN? Just a quick recap. The first one was that you see there's a CNN, okay, and there are 2000 region proposals. Many of these are overlapping, which are fed separately to the CNN. Means first you feed the first one, then the second one, then the third one, and so on, and then you feed the last one. So it means you are feeding 2000 regions separately to the CNN. Means 2000 forward passes per image, which is a bit too much, right? So this was one major drawback. Other than that, when you are training this, you have to train three different models. The first is that you have to fine tune the CNN, right, to produce the feature. And then the classifier is an SVM, so you need to train SVM as well to recognize the classes. And then the regression model, which is predicting four numbers, you also need to train them, right? So it means you are training the CNN, you are training the SVM, and you are training the regressor as well. So you see, these three trainings make it very slow, but you can say, okay, training is one time job, so I'm not too much bothered about these, right? But at the test time, even you have to do this. You have to feed 2000 proposals to the CNN. It means 2000 forward passes. So even at test time it would be slow, even if we ignore the training part, right? So in order to address these issues, as I told you, in the very next year, Fast RCNN was introduced. There were many aspects which were improved, but the two key aspects of Fast RCNN were that instead of 2000 forward passes, the CNN is fed only with one single image, right? Means you only feed the image once to the CNN. And then there's a concept of ROI pooling that I will share with you in the subsequent discussion. ROI stands for region of interest pooling, right? So this was one of the key ideas. The second one was that instead of having a separate classifier, which was SVM in RCNN, and then a separate model for regression, they combine the bounding box regression and classification in a single network, just like we had seen in case of object detection plus localization, that you have one network which has two branches. One branch is performing classification, while the other branch is giving you four numbers by using regression, right? Okay, so this is a summary of what I'll be explaining in the subsequent discussion, right? That overall approach is similar to RCNN, but rather than separately feeding the region proposal to the CNN, the complete image is fed to the CNN only once. So when you feed the input image to the CNN, it will convert the image into a feature map. Okay, now let me just explain this on the board so that you understand. So you will have an image, okay, maybe it has some objects like maybe a chair, okay, maybe a person and a car, something like that, okay. So you will feed it to a CNN, and the CNN will give you a feature map, right? This is some feature map which has some you can say width, height, and dimension. And you are also feeding this to selective search, okay, and selective search will produce region proposals, right? It will give you different boxes that, okay, it thinks that some object can be present in these boxes. right? So it is like that. Okay, now the idea is that you see, suppose this image was 100 cross 100. Okay, but once you pass it through CNN, you are doing pooling, you are doing convolution, so the dimension would not be 100 cross 100, it would be maybe say 10 cross 10 cross 50, right? 50 is the depth. Maybe in the last layer we were using 50 features, sorry, 50 filters, so it would be something like that. Now this is the image on which you have region proposals which have been generated by selective search, that okay, these are the regions in the image where some object can be present. Now what they suggest is that you project these proposals on this feature map. Now what does that mean? It means that, for example, if there is a box here, okay, maybe this one which I'm talking about, and suppose the location or the center point of the box is say 50-50. Okay, this is the x and y coordinates of the center point or the left corner, whatever convention you are using. So you have a box at 50-50, and say the height of the box is say 40, and the width of the box is 60. Okay, so this is a box which is at this location with this height and this width. Okay, so this is the box that we are talking about. Now you can project this box on the feature map by taking into account the downsampling. Okay, for example, original image was 100 by 100 and the output is 10 by 10. So you have gone from 100 cross 100 to 10 by 10. It means the factor, downsampling factor, is 1 by 10, right? Because the output is 1/10 of the input. Okay, you simply divide these two and you get this factor. So it means that a point which was 50-50 in this image, where will that point be in this feature map? You simply multiply it by the downsampling factor. So it means whatever this point was 50-50 in the original image, now it is somewhere here, and this point is 5-5 in the feature map. Okay, you simply multiply and you get it. And similarly, if the height was 40 in the original image, then h prime would be 40 cross 1 by 10, that is 4. It means here it's you can say height would be 4 and width would be 6, something like that. Okay, so in other words, we have a box in the original image, we are projecting or mapping it on the feature map, that where this box would be in the feature map. Okay, so this is the key idea. Now I'll go back to the slides and then repeat this idea so that you understand fully what we are trying to do here. Okay, so you see what we are doing, that this is the general idea, that you have an image, you are feeding that image only once to the CNN. Okay, and at the same time you are feeding this image to selective search. Selective search is generating some proposal, some boxes on this original image. Okay, and then you are projecting those boxes in the feature map, that okay, if I have a box here in the image, where is this location in the feature map? You can easily compute by taking into account the downsampling factor. So you say, okay, this box in the original image corresponds to this particular box in the feature map. Now you see the advantage, that instead of feeding 2000 separate boxes to the CNN, you just feed once the image, you have the feature map, and you directly map the region proposals on the feature map. Now once you have this region proposal, then you have another new concept which was not present in our CNN, which is called ROI pooling. I will explain it later, but I'm just giving you the global picture, that you see, once you have fully connected layers in the network, it means you have a fixed number of neurons here. Okay, suppose you have 100 neurons, so it means everything should be of fixed size, but the region proposals are of different sizes. Okay, so this layer will convert all of these region proposals in a smart way to a fixed size, rather than reshaping them, right? It will do something else which I will explain later, so that all of these boxes are of fixed size, say 10 by 10. Okay, so you have 100 neurons here, so you can easily feed them to the fully connected layer. And then instead of having an SVM classifier, you see, now we don't need to train separately an SVM, because all of these layers, once they are learned, this is your classifier part, which is a softmax layer, and then this is your regressor part, which will give you 4 numbers which are the x, y coordinate and width and height of the bounding box, right? So this is the general overview. I'll explain it in detail slowly so that we get to know every step in detail, right? So as I told you that fast RCNN will receive region proposals from some external system like selective search, which was used in the original paper. These proposals are mapped on the feature map, and then there is an ROI pooling layer which will resize all of these regions to a fixed size, right? Because the fully connected layers require a fixed size. And the advantage is that different sizes are now mapped to a fixed length in a smart way, right? How this happened, we will see later. Okay, now let's come back to the mapping, that how we project, you can say, region proposals on the feature map. Okay, so suppose we have these two region proposals in the original image, which is like 100 cross 100. Okay, this is proposal 1, proposal 2. When you pass the image through CNN, okay, sorry, CNN, you get feature maps. Okay, so this is one feature map, one small square, then second small square. Okay, so actually we represent them in a volume like this, but since we have to visualize them, so if we represent it like this, you will not be able to see them. Okay, so this is actually one filter, second filter, third filter. So one small square is the output of one filter, and the size is small. Why size is small? Maybe the size is of this one box is say 10 by 10, because we are doing pooling, we are reducing the spatial dimensions as we always do in a CNN, right? So these are the activations on the last convolution layer. Maybe this is what we are visualizing here. Okay, now you see, if these are the two region proposals, then we say where these are in this feature map. So I pick one feature map, maybe this one. Okay, but of course this is a volume. So if this is a box which was at location say 8080, okay, this center point was 8080. So what will happen now? The center point, this one would be 88. Why 88? Because we are assuming that this image was 100 cross 100, and after passing through all convolutional and pooling layers, the feature map is 10 cross 10, right? So the down sampling factor is 10. So you can easily project that if this is the red box number 2 in the original image, where I will have this in the feature map. Okay, you just need to do that. And these are the same calculations which I explained a little earlier, so it can serve as a revisit. So suppose you are resizing an image. Okay, image is very large, say 1024 by 1024, you resize it to 128 by 128. Okay, so now what is your ratio in x dimension and y dimension? You simply divide the new dimension by the old dimension. Since x and y ratio can be different, in this example they are same, but of course they can be different because image is not always a square. Okay, so x ratio is 128 by 1024, which I think should be, you divide them, I think this should be 1 by 8, something like that. Okay, so now what you see, that if you have a point say 8080 in the original image, and you want to see where it is in the new image, so you simply multiply it by the ratio, which is 1 by 8, so you get 88. Okay, sorry, not 88, 1010. Okay, so 80, the point 8080 in this big image, say this is 8080, it maps to 1010 in the new image, right? And same you can do for width and height. So if we generalize it, we have an original x, original y. Okay, and then we have new x, new y. We can compute the x ratio, which is new x by old x or original x. Similarly, we can compute the y ratio. And if you want to see any point xy, where does it go, you simply multiply x by x ratio and y by y ratio. So you can find, if I have a big image and a small image, and there is an object, so where this object would be in the smaller image, right? This is a very standard way of projecting or mapping a high dimension to a lower dimension, right? Okay, now this is again the same thing, that this is the feature map. Okay, we are doing it on the complete depth, but for discussion purposes, we are illustrating it with only one feature map. Okay, so this was a feature map. Okay, I have shown it here in an enlarged way so that you can see. And suppose this was our original image, okay, where we had two proposals here. So now we we take into account the downsampling factor, and we project those proposals on the feature map. Okay, so this is proposal number 1, this is proposal number 2. So you see now what we are doing smartly, that instead of feeding separately each region proposal, in our CNN we were feeding this to CNN and we were getting this, then we were separately feeding this and we were getting this. Okay, so we were doing it 2000 times. But now what we are doing, we are feeding image to the CNN, we are getting feature map, we are also feeding image to selective search, and we are simply projecting the region proposals on the feature map. So this is, you see, a very big gain, that instead of feeding each box separately to the CNN and then computing these boxes, means these activations 2000 times, now we have to do it only once. Okay, so this is the general idea of mapping, right? So if you have any confusion related to mapping, please let me know, and then I'll move to the ROI layer. Okay, because we'll go stepwise, because if you miss one of the steps, then the subsequent steps will not make much sense to you, right? So if the mapping is not clear, please let me know so that we can discuss it in detail. Okay, now I'll quickly introduce you to the next concept. We'll see it in detail in a while, right? But I'll just give you the general idea, which is ROI pooling. Right? ROI stands for region of interest. Okay, so you see, your region proposals would be of different sizes. Something is like this, something could be this, or something could be this. Okay, and suppose I want to map each of these to 2 cross 2. Okay, so it means I want to go from here to here. These are of different sizes. I want to map each of these to 2 cross 2, right? So you see, in general pooling, what we do is we have a filter, we have a window. Okay, for example, if the window is 2 cross 2, so maybe I will have small windows like this. Okay, 2 cross 2, 2 cross 2, and so on. And I will pick the maximum value in each 2 cross 2 window, and then I will have the output, right? So for example, if I do that here, by a 2 by 2 filter, how many windows do I have? 1, 2, 3, 4, 5. Okay, 6. So it means my output would be 2 cross 6. If I do the same thing here, so maybe I have 1, 2, 3, 4, and maybe assume 6 here, so my output could be 6 cross 4. And if I do the same thing here, so maybe I do pooling with 2 by 2 window, so I end up with 3 by 3. Okay, so if you are doing pooling in a conventional way, you have a window size which is like 2 cross 2 here. If you do pooling with a 2 by 2 window on boxes of different sizes, then you are ending up with different dimension, right? Means this box will produce 6 by 4, this will produce 2 by 6, this will produce 3 by 3. So instead of doing that, what we'll do, as I'll explain to you, that if I have boxes of different sizes, okay, and I want 2 by 2 output, so instead of making a window, what I will do, I will divide my box in a grid of 2 by 2. Okay, whatever is the size of the box, I divide it into 4 cells. Okay, so it means that this would be different for every box. My objective is to have a 2 by 2 grid in each of these boxes, and from each grid now I pick the maximum value. So you see, this will map to 2 by 2, this will also map to 2 by 2, and this will also map to 2 by 2. Okay, so this is the general idea. We'll see it in more detail in a while. Okay, so let's now see in more detail ROI pooling, right? So let's do a concrete example of how ROI pooling works with some numbers. Okay, so let's say we have a proposal which is maybe not 10 cross 10. Okay, means there are 10 rows and 10 columns. And then we have another proposal which is like, say, 4 cross 4. Okay, and at the next layer, right, this is layer L minus 1, say this is L, we need 4 values, right? We need a 2 by 2 output. Okay, so it means that 10 by 10 should also map to 2 by 2, and 4 cross 4 should also map to 2 by 2, right? So what you need to do is, your target is 2 by 2, so for this one you say 10 by 2, which is 5. Okay, so it means we will have a window of 5 cross 5 in this image. It means you have 10 rows, so you divide them here, so you have 5 rows here, 5 rows here. Similarly, you have 10 columns, right? So you have 5 columns here and 5 columns here. Okay, so you see this one block is 5 cross 5. And how many grid cells do you have? We have 1, 2, 3, 4. Now let's do the same thing here, where original matrix is 4 by 4, target is 2 by 2, so I get 2. So it means I have 4 rows, I divide them into 2 plus 2. I have 4 columns, I divide them into 2 by 2. So my each box is 2 cross 2, and still I have 4 boxes, 1, 2, 3, 4. Now what we'll do, from this region I pick one maximum value, we are doing max pooling, and that comes here. Similarly, from this you pick the max value, which will come here, and the same you repeat for each of the 4 cells, and you will have 4 values. So you are applying max pooling, but now you see the size here of window was 5 cross 5, and here it was 2 cross 2, because now we are not fixing the window size, we are changing the window size depending upon what is the size of the region, so that eventually we always get 4 values. Okay, here the window was 5 cross 5, here the window is 2 cross 2. But the good thing is that both of these are divided in a grid of 4 cells, right? So this is the new, you can say, idea which was introduced by this ROI pooling layer, which will ensure that whatever is the size of proposal you are getting, you always end up with a predefined size. Okay, now let's do a different example, because these numbers were very nice. They actually rounded, they gave you integer when you were dividing. Okay, so suppose we have a region proposal of 5 cross 7, okay, which is like odd numbers, and we want an output of 2 cross 2. Okay, so it's the same thing. What you will do, you will simply divide them together. So if I do 5 by 2, it is 2.5, right? So 2.5 can either be 2 rows or 3 rows, depending upon what we need. Okay, so just keep this in mind. Similarly, when you do 7 by 2, you get 3.5. So 3.5 you can take as 3, or you can take as 4, depending upon your requirement, right? So now we have choices for rows, that I can take 2 rows or 3 rows, and I can take 3 columns or 4 columns. So let's see this example, which is slightly more complex as compared to what we have seen, and then we can discuss further. Okay, so maybe this will explain it. Okay, so this black box that you see here, this is our region proposal. Okay, and the size of this proposal is, it has 5 rows and 7 columns. Okay, so when we did division, we said, okay, rows, I can divide rows into 2 rows or 3 rows, because we get 2.5. Okay, so first I divide it like this into rows. So you see the upper part has 2 rows, the lower part has 3 rows. So now I have covered all the 5 rows. Similarly, for the column, we say, okay, I pick maybe 3 columns, 1, 2, 3. So I divide it like this. Okay, so now this has 3 columns, but this one has 4 columns, which is okay, right? Which is okay. The whole idea is that now my region is divided into 4 parts, and from each part I will pick the maximum value, and I will end up with 4 values, or a 2 by 2 matrix, right? So just see another illustration. This was our image. This black one is the region proposal. We divide the region proposal into a grid of 2 by 2, and then from each cell in the grid we are keeping the maximum value, right? So maybe here the maximum was 0.85, then 0.84, 0.96, and 0.97, and eventually we end up with the 2 by 2 matrix that we required. Okay, so now let's go back and see what we have achieved so far, with some insights into or you can say a recap of the steps that we have been doing. The first thing was that we are feeding the complete image to the CN and not the individual regions, which eventually allows shared computation and help us save a lot of time, right? And then once we have the region proposals, we project them on the feature map, And we use ROI pooling layer, and the advantage of ROI pooling layer is that it will end up with a constant number of bins. Means if you have fully connected layer, you can feed them by smartly choosing the window size. You can always get a fixed size vector or a matrix, whatever is needed at the fully connected layer. Then, as we said, that as opposed to RCNN, it is you can say single network which jointly trains the classifier part as well as the bounding box regressor part, right? So just like we had seen in classification plus localization, your network will have two branches. One branch is for classification, which is softmax. The other branch is for regression, which is giving you four numbers and an output. So you have a multitask objective function or the loss function. Means you have a classification loss, you have a regression loss, which is combined together when you back propagate it and learn your weights. So this is an illustration. I think it is from their original paper. I can't recall, but I think yes, this is from their paper, which gives you the overall flow of what is happening. You feed your image to a CNN, deep CNN, and this can be anything, right? It can be a pre-trained network, VJG, RESTnet, anything which you choose. So you are feeding your image to a CNN, which is generating a feature map, right? So this is the feature map you get. And then you are also feeding this image to selective search, which is giving you region proposal. So what you do, you project those proposals on the convolutional map that, okay, this is my one region, second region, and so on, right? And then you have this, the ROI pooling layer, which is resizing every proposal to a fixed size, right? Then you have a couple of fully connected layer, and then these are the two branches. You see, this is the classification branch with the softmax loss function, and this is the regression branch, which will be giving you the location of the box. So this is something which is similar to what we have already seen once we were looking at classification plus localization, right? So now you see you have one end-to-end trainable system because you have a multitask loss function. You do not have to train the classifier separately and the regressor separately as it was happening in RCNN, right? So that's why you gain a lot of time. Now this is a good comparison. Again, it's I think from their paper. I can't recall exactly. We have not seen SPP net, so you can ignore this part, right? Now let's see first the training time. So for training, RCNN was taking 84 hours, right? It is, I think, around 3.5 days. You can say, okay, it's manageable because we have to do it one time. But fast RCNN is only taking like 9 hours, right? It means it is one working day. You launch training at 9 a.m. in the morning, and by 6 in the evening, once you go back home, the network is trained. Okay, so you see, we are gaining a lot in training time. But you can argue that training time is not important, it is the test time important. So let's now compare the test time. Okay, so you see, for RCNN, if we include the time of region proposal, the selective search, so for one image it was taking 49 seconds. Okay, and if you exclude the region proposal time, it is taking 47 seconds. So in other words, the selective search is taking 2 seconds. Okay, around 2 seconds. Now let's see this. So you see, fast RCNN with region proposal is taking 2.3 seconds only. Means 49 seconds is reduced to 2.3 seconds, which is a lot of gain. And similarly, if you exclude the 2 seconds of selective search, then actually the detector part is only taking about zero point 0.3 seconds. So now you see, in fast RCNN, the total time is 2.3 seconds, and the detection network is only taking 0.3 seconds, and 2 seconds are being eaten up by the selective search. You see, which is, if you compute the percentage, so it's a big chunk of time, right? So this is something which bothered researchers, and as we'll see shortly, then people actually thought, okay, the network part is fine, how can we reduce this 2 second even further, right? That we'll see shortly. So concluding the comparison between RCNN and fast RCNN, right? So the biggest is what you visually see here, that you are feeding every box separately to the CNN. So you are having 2000 forward passes. So you see, already a very big gain is that you only feed image once, and you map or you project the region proposals directly on the feature map. Then you have ROI pooling layer. Okay, and then you have fully connected layer, and then you have two branches, one for the classification and other for the regression, right? So this is a visual comparison which helps you understand the differences between two. So but as I told you that in case of fast rcnn, the selective search is taking a lot of time. When you say, when you see 2.3 seconds is the total time and 2 seconds are for selective search, then of course there is a temptation that somehow we should get rid of selective search and do something better. So that we'll see in the next detector, which is faster rcnn. But before that, if there are some discussion points, we can spare some time on that. Thank you.